When you chat with modern AI, you get an eerie feeling that a conscious mind is staring back at you. But the reality is entirely mechanical. These systems have zero subjective experience, zero emotions, and absolutely no understanding of the words they generate, which leaves us with a compelling mystery. If these servers are completely devoid of thought, how are they so incredibly good at sounding exactly like us? Modern artificial intelligence relies on a sophisticated form of biological mimicry to bridge that gap. Meet Buddy. Buddy is a parrot with an exceptionally sharp memory who spends his days listening to his owner's conversations and perfectly mimicking them. When Buddy hears the phrase, "I'm feeling hungry, I want some," he immediately squawks biryani, or food. He doesn't do this because he knows what biryani tastes like, but simply because he has heard those words follow that specific phrase most often. Researchers call this behavior a stochastic parrot. The word stochastic describes a system driven by statistical probability and a bit of randomness to guess the next word in a sequence. Understanding how these models work starts with viewing them through the lens of this simple, unthinking bird. You already use digital versions of this parrot every day. Tools like Gmail autocomplete function the same way, predicting your next word based on past patterns. The engine is a neural network processing numbers, not concepts. It rapidly scans the preceding sequence to calculate the mathematical likelihood of what appears next. It assigns a strict probability score to thousands of candidates, selecting the word with the highest statistical chance. At its core, conversational AI is high-speed statistics functioning as fluent language. Imagine our parrot suddenly gains super hearing, listening to every Wikipedia article, news site, and published book across the entire globe. This creates a large language model, or LLM. Processing this massive volume of data requires a digital architecture containing trillions of parameters. This staggering volume of parameters allows the neural network to map out the mathematical relationships between words, capturing regional slang and the hidden contextual rules of human communication. Internalizing these massive patterns, learning the structure of a poem, the vocabulary of a nutritionist, recreating formats word by predicted word. The illusion of intelligence is a byproduct of this scale. A larger parrot is still just a parrot. But there is a downside to this scale. When an AI learns from the internet, it inevitably absorbs the abusive, toxic, and dangerous human behaviors present in that data. If Buddy starts repeating toxic language he overheard in town, his owner has to step in, punishing the bad phrases and rewarding the safe ones. Companies manage this through reinforcement learning with human feedback, or RLHF. They hire thousands of human workers to manually review and correct the AI's toxic outputs. These interventions steer the probability engine, lowering the mathematical likelihood of generating harmful text. Human feedback acts as the steering wheel that tames the raw mathematical engine, making it safe for public use. The true anatomy of a large language model is a hyperscaled, probability-calculating, heavily filtered text prediction engine. Despite its convincing fluency, there is no consciousness inside the server. It feels no emotion, and there is nobody home. Understanding this mechanical reality changes how we interact with these systems. We can stop expecting them to reason like humans and start utilizing them for what they actually are: powerful pattern recognition tools. Removing the magic from the machine reveals what it actually is: a specialized system for predicting and processing the vast landscape of human language.